Hello everyone, my name is Alithya Hussain. I'm the team leader for our team ScienceSurf, and our problem statement ID is SIH25104, and our problem statement title is Language Agnostic Chatbot. The theme of our problem is smart education and its category is software. Now I'll move on and explain more about the ideation and technical approach of our solution. Uh, what we ideated to build is to build a modular chatbot which could easily be embedded onto the college website such that it can be easily put on the front end of any college website. And also, the chatbot would facilitate the automatic scraping for that website, and the automatic scraping would extract all the documents, all the media link documents and PDF documents for important papers such as notices, circulars, registration form, hostel forms, and many more. And all of these important documents are then converted into text and processed and then finally kept in the knowledge base. Now, so for every college website, we create a knowledge base. Now when a user comes to the website, they would first sign up into the chatbot, then they would log in, and after that, they would put in their query in any of the regional language they prefer or English. After typing in the query, the chatbot would access the knowledge base and use it as a context to answer the user's query. And the chatbot would also answer in the same language in which the user query asked in. After that, if the user query does not find the answer suitable, it can call the staff of the college and clarify their queries there, or uh, or they can go to Telegram or MS Teams where our chatbot would also be present. Now, after that, let's take a look at the technical approach for our idea. So we can break down the technical approach into two stages. The first stage is pre-processing, and the second stage is inferencing and querying. So the pre-processing stage would occur when the chatbot detects when the chatbot is embedded onto the front end of the college website. It would detect the base URL of the website. After detecting it, it checks if that URL has any data in the knowledge base. If it has no data at all, then the scraping process starts. Now, what happens is first at the homepage of the website, we use Beautiful Soup, a Python module, to get the HTML elements, and we look for the anchor tag element, which is kind of the link element, which links to different pages or different PDFs and links. So we look in them, and then we go inside each of these links, and we look for all the links present in these links. So supposedly I'm at the home page, and a link is pointing towards About Us. Then I go to the About Us, and then I look at all the links present there. Now after that, we get a huge collection of links. Now we filter these links and get only the media links, and after that, we convert these media links into PDFs using LibreOffice or some other module, and after converting them into PDF, we convert them into text. We call this process text extraction. And then we chunk these text documents, or we chunk these text values. And then finally, these chunks are converted into vectors using a multilingual embedding model. So after the vectors are created, these vectors are saved in the database, which we call as the knowledge base. Now, this was the pre-processing part, and it only occurs when the scraping occurs during when a background scheduler is run, or when the college is added in for the first time. So supposedly some college A is added for the first time, then this process would happen. And if it happens for the second time, it won't happen again. Now, the second part of the technical approach is querying and inference. So what happens is a user would ask in the query in any of the languages, supposedly English or any regional language of India, Marathi, Punjabi, anything, Odia, Bengali. So what would happen is that query would be converted into a vector embedding. Now, this vector embedding would be compared for similarity score between all the vectors present in the knowledge base. Now, all the vectors, the term all the vectors can be used loosely here, since there are multiple indexing methods which which do not compare all the vectors. So, and it also comparing all the vectors increases our time. So, we will probably use HNSW, hyperspace navigable workspace, for our indexing method. So what happens is that the embedding of the user query is compared with all the vectors in the knowledge base, and the all the vectors which are the most similar, all the top k similar vectors are returned, and these vectors have attached to them some text value. So we get the chunk text value of these vectors, and we give it to the LLM as context to answer this user query. Now the LLM gets the chunk text and the user query as context and user query, and then it answers the user query back in the original language in which the user asked in, and the final answer is given to the user. So supposedly, a person a person Alice enters a user query in Odia, saying that they want a computer engineering syllabus. Now it would look in the knowledge database, and then it would probably return some computer syllabus chunks. Now these chunks are given to the LLM, which in our case is a multilingual LLM, and our embedding model is also multilingual. So both of these processes would be multilingual, and the LLM would get the chunks, receive chunks of computer syllabus, and it would also get the user query in Odia or whatever language they wrote in, and it would get that. And after that, the LLM would give the answer back in the same language. Now, this whole process is called querying and inferencing. The querying part is the user query and the vector results and all. And the inferencing part is just the part where the LLM is getting the context, user query, and is generating an answer. That part is called inferencing. Thank you.
So let's talk about feasibility and viability. Our solution is highly feasible because it builds on proven technologies like RAG pipelines, speech vector, OCR, and multilingual LLMs. We avoid costly translation APIs by directly using multilingual embeddings, making it both faster and more affordable. The chatbot is modular, so colleges can easily integrate it into their existing websites while also being accessible through Telegram and MS Teams. And in terms of viability, the demand is very real. Colleges struggle daily with multilingual communication and repetitive queries. By deploying our solution, students get 24 into 7 support in the regional language, staff save time, repetitive questions, and institutions benefits from scalable, low maintenance AI support. It is cost effective, inclusive, and can be maintained even by students after this hackathons. And of course, there are challenges such as accuracy in multilingual retrieval, latency with large databases, and adoption resistance. But we address these with fine-tuned embeddings, caching for speed, fallback mechanism, and secure authentication. This ensures the system is not only feasible